Hello everyone. In this chapter we're going to learn about graphing equations of lines and linear models, and we're also going to see how they tie in with the concept of rate of change. We'll start out by learning about graphing equations of lines and linear models, and then we'll move into rates of change after that. First, we'd like to talk about some vocabulary that you'll encounter when dealing with uh, equations and later with functions. So, when we deal with equations and we talk about the solution of an equation, if we look at a real simple equation like, say, x plus 2 equals 5, right? So when we say what is a solution of this equation, we just want to look for the value of the variable that makes the equation true. And of course, without knowing too much about algebra, you know that that would be 3. So we say x equals 3 is a solution of x plus 2 equals 5 because it makes it true. How? Well, let's just take 3 and substitute it for x up here, right? And we get 3 plus 2. We want to know if that equals 5. And of course, 5 equals 5. So we can see that x equals 3 makes this equation true. So that's why we say x equals 3 is a solution. Another way of saying that is to say that x equals 3 satisfies. This verb satisfy can be used to describe a solution. We say x equals 3 satisfies the equation x plus 2 equals 5. So when you hear that terminology, it has nothing to do with satisfying, such as a delicious ice cream or anything like that. It just has to do with the fact that it makes the equation true. And when you're dealing with linear equations in two variables, of course, you're going to have two variables involved. So if we have the first one example we looked at was a simple linear equation, just to remind us of what a solution means. But now if we move on to two variables, such as y equals x plus 2, the solution of this kind of equation, of course, is not just going to be one number such as the 3 we had up here. The solution of this equation is going to have two variables represented in it, values for two variables. So we put that in the form of an ordered pair, such as, for example, if x is 1, right, you get y equals 1 plus 2, which is 3. So here is one solution of such a linear equation in two variables. Notice that linear equations in two variables such as this are not just going to have one solution. They're going to have infinitely many solutions. For example, I can let x be some other values, such as, say, 5, right? Notice that y is just going to be 5 plus 2, which is 7. So notice both of these ordered pairs satisfy this linear equation in two variables, right? So we say that both of them satisfy it, or both of them are solutions of that equation. Notice how the solutions are ordered pairs. You always write the x value first, or the explanatory variable first, and then the y value or whatever the response variable may be. So to see if we can identify solutions of an equation, consider this. We want to know if 2, 1, the ordered pair 2, 1 is a solution of this linear equation. Well, remember, 2 represents x and 1 represents y. So we substitute 1 for y and 2 for x. So we have 3 times 2 minus 5. And of course, we put a question mark above that because we're not claiming, we're checking, right? So we want to know if 1 is 6 minus 5. And of course, in the next step, I'm just going to write 1 equals 1, and we don't need the question mark anymore because we verified that this ordered pair with x being 2 and y being 1 does satisfy this linear equation in two variables. Therefore, the ordered pair 2, 1 is a solution of the equation. So that would be our answer, yes. Is 4, 9, the ordered pair 4, 9, a solution of this equation? You should pause the video, go see if it is or not, and then come back to watch the rest of the video. All right, so I hope that you substituted 9 for y and 4 for x, right? And you did have a question mark while you were checking above the equal sign, right? Because we don't know if it is or not. So we're asking, well, let's see, that's 12 minus 5. So again, we still need our question mark. And then we get to 9 equals 7. Okay, now that is false, right? In fact, that statement, since it has no variables in it, is always false. Such a false statement we call a contradiction, actually. So this means the ordered pair 4, 9 does not satisfy this linear equation in two variables. Therefore, no, it is not a solution of that equation. Next, we want to look at what is meant by the graph of an equation in two variables, such as, say, y equals x plus 2 that we looked at earlier. What we mean by that, basically, is the set of all the solutions of such an equation. Let's go take a closer look in a blank whiteboard. Okay, if you recall from what we talked about a minute ago, when you look at an equation like y equals x plus 2, you don't have just one solution. You have many, many solutions. In fact, you have infinitely many solutions. If we look at a few of them, for example, if x is 0, you get y equals 0 plus 2, which is just 2. If x is 1, you get 1 plus 2, which is 3. If x is 2, you get 2 plus 2, which is 4, etc. 3 will give you 5. And remember, this doesn't just work for nice whole numbers. You can have any real number in there, right? So for example, if I have x equals 1/2, right? For example, y would be 2 plus 1/2. So it would be 2.5 or 5/2. If x, for example, is square root of 2, right? Y would just be square root of 2 plus 2. So don't think that you only have the nice whole numbers represented on this side, right? And or they don't all have to be positive either. For example, I can have -3 for x, and I get y equals -3 plus 2, which is -1. Or you could have -2, which will give you 0, etc. These are just a few examples, right? So if we plot these in a grid, we'll notice something interesting, and that is the fact that if you look at the points, so the ordered pair, for example, 0, 2, right? So remember that this first solution can be represented using the ordered pair 0, 2, this one using the ordered pair 1, 3, this one using the ordered pair 2, 4, etc., right? So if we just do those few, so 0, 2 will be right there, 1, 3 will be right there, 2, 4 will be right there, right? Even if we do some negative ones, -3, -1, so -3, -1, -2, 0. Notice what happens? They all line up. So, and this is not surprising. This is always going to happen with equations of this type when you have y equals mx plus b. That's a linear equation in slope-intercept form. We'll learn about those concepts more as we proceed, but one form of lines or linear equations is this slope-intercept form. Another one is ax plus by equals c. This one is standard form. Now, any equation basically in which you have just the first power of y and the first power of x can be put into both of those forms, right? Of particular interest to us is this form, the slope-intercept form, because as we'll see, it is the functional form of the equation of a line, and it's also very useful for us in this statistical concept because this will be the response variable and the x here will be the explanatory variable in such equations. If we draw the straight line that clearly goes through those points, we will see the linear function that would be represented here. So let me see if I can get this any closer. All right. Like so. Okay. So notice that all these other points, even these less than simple forms, more complex numbers such as square root of 2, or you can even have pi as an input, etc. They will all have a representative on this line, right, in the form of an input-output pair. So basically, when you talk about the graph of this kind of an linear equation in two variables, you're talking about the set of all solutions of this particular equation, right? So if it's a solution, it needs to be on the graph. And if it's on this graph, you can be certain that it's a solution of that linear equation. So it works both ways. So just to reiterate, the graph of an equation in two variables is a set of all points that correspond to the solutions of the equation. Any point that is a solution of the equation must be on the graph, and any point on the graph must be a solution of the equation. So here we're going to find 5 solutions of this particular linear equation. Y equals 2x minus 1. So basically we can make ourselves a table. Now notice that we could use any value we want for x and find the corresponding y value, right? Given that no specific instructions are given, we'll just pick a couple of simple numbers, like say we'll start with 0 in the middle. They'll maybe do a couple of points less than 0 and couple of whole numbers greater than 0 to get our 5 solutions. If they had more specific instructions, we would have adhered to them, but since they don't, we'll take it easy. So for example, when x is -2, we're going to get y equals 2 times, see, y equals 2x minus 1. So we get y equals 2 times -2 minus 1. So we get y equals -4 minus 1, or y equals -5. So there it is. There's one solution. When x is -1, we get y equals 2 times -1 minus 1. We're just substituting -1 where we see x, because that's what we're substituting for. So we get y equals -2 minus 1, or y equals -3. If x is 0, we're going to get y equals 2 times 0 minus 1. So y equals 0 minus 1, or y equals -1. When x is 1, we're going to get y equals 2 times 1 minus 1. So we get y equals 2 minus 1, so y equals 1. And when x is 2, we get y equals 2 times 2 minus 1. So we get y equals 4 minus 1, or y equals 3. So for -1, we can put -3 in here. For 0, -1. For 1, we put 1. And for 2, we put 3. All right, so notice that an increase of 1 in the x values corresponds to a double increase in the y region here. All right. Now, if you're going to represent the solutions, you're going to represent them as ordered pairs. So there is one solution. Here is another one. There's our third one, our fourth one, and our fifth one. Okay? And that's all there is to that. Now, if you take the solutions that we found and plot them on a grid, just as we did on that previous example of y equals x plus 2, you'll notice that these will also line up perfectly in a linear fashion. Okay, so this is, again, not surprising. All equations that can be put into either of these two forms, y equals mx plus b or ax plus by equals c, are going to be represented using a straight line when you graph them. In other words, when you plot all their solutions, they will line up perfectly. All right, so here we're asked to graph this equation and also find the y-intercept. Now, just looking at it, we can see it's in the form of y equals mx plus b, so we know it's going to be a straight line. So if somehow it doesn't turn out a straight line, we know we made some kind of an error in our table creation, right? So if we go ahead and plot the points that we can organize in a table. Let's go ahead and make the table x, y. All right, so here again, the thing that's important to understand is that while you can, plot as many points as you want, the question is, how many do you actually need, right? That's where a very important fact about lines it needs to be understood, and the fact can be stated like this. It's a very nice, simple statement. It says 2 points in a plane determine a line. Okay, so what does that mean? That means if you have a plane, like the surface of the computer you're working on, of course, extended infinitely in every direction, or the whiteboard that you may see in a classroom, that kind of a plane, two-dimensional plane, and you have 2 points on it, right? Then there is one and only one straight line that will go through those 2 points. That's what this strong word determine here means, right? So if you're given two, and if we want to be really, really mathematically precise, we'll say 2 distinct points. in mathematics, we always want to make sure we've covered all possibilities. And of course, here there's the possibility that the 2 points could be the same point. So to make sure that we don't fall into that trap, we just say 2 distinct points and then everything goes well. So 2 distinct points in a plane determine a line. So what does that really mean? If we want to translate into practicality, it means really all I need to get a perfect graph of this linear equation is just 2 solutions, because all other solutions are going to go through the line that will go through those 2 solutions, right? So here I'll just do 2 really simple values, like I'll do 0 and 1. So if x is 0, notice we get negative 2 times 0, which is 0 plus 3, so that gives us 3. If x is 1, we get negative 2 times 1, which is negative 2 plus 3, which is 1, right? So all I need is to plot those 2 points, and I'll have my line that I'm trying to graph. All right, so we'll utilize this grid. So we're going to have 0, 3. So we know that's right there. This pen cooperates. And 1, 1. Okay, so of course we'll draw the straight line that will go through those 2 points. I'll try to make this work as well as I can. All right. Okay, so you get the idea, right? This is going to be hard to get precise. All right, so like that. There is the straight line that goes through, so that would describe this particular function right here, or a linear equation. Actually, we haven't really described them as a function yet, but it is. Of course, remember that you get arrows on both ends because that line will go on indefinitely. It's never going to end. In other words, the number of solutions is infinite, so that line is not, that line segment that we see initially is not the entire graph. All right. So we were also asked to find the y-intercept. Remember, the y-intercept is the place where the line crosses, is the point of intersection of the line and the y-axis, right? So it's that point right there, right? So remember, of course, for every point on the y-axis, we know that the x value is 0. So when we set x equal to 0 and found that y value, we in fact were finding the y-intercept as well. So that is the y-intercept itself. Okay? And you're going to always realize clearly this will always happen, because whenever we have y equals mx plus b, that's a very generic equation for a line, right? Notice that whenever x is 0, right there, m times 0 is going to be 0. So when x is 0, we're always going to get y equals b, right? So 0b is always going to be the y-intercept of a line determined using an equation of this form. So in that form, now it would be incorrect to say that b is the y-intercept, because remember, you're in the plane, and in the plane you don't talk about any point with just one value. You always have to give an ordered pair. So the correct language to use would be that the ordered pair 0b is the y-intercept, okay? So in this case, of course, the ordered pair is 0, 3. So here we will repeat that fact. The y-intercept of the graph of y equals mx plus b is always going to be the ordered pair 0, b. Of course, that is not something you just want to memorize because it's so easy to understand, right? You never want to overcrowd your mind by things that you can understand, right? But after you use it a few times, it just becomes second nature. So understanding should always come first, and remembering should always follow it like a shadow. The understanding will help you do the problems, and as you do them, the repetition will easily make you remember them. So again, it's always remembering that should follow understanding, and understanding should come first. Many students unfortunately get that backwards. They try to memorize concepts, right? And then within a day or two, they've forgotten everything, because understanding has depth, right? So when you understand something, it forms some very powerful neuronal connections in your brain, right? And those last, right? It's like when you really understand something, 20 years later, a relative can ask you a question and you'll answer it. But when you memorize it, you've noticed it in classes that you've gone through with just memorizing. By the time the break is over and you go back the next term, you don't remember anything. So if you that's the way you've been approaching education, and it doesn't matter if it's a math class or even a history class, right? Even if in a history class where you think it's all memorization, it's not. When you understand the relationships between events in a history class, you'll also remember those much more easily. So notice the lines that we have seen so far have all been what we call oblique. That means not vertical and not horizontal, right? They've always had some kind of a slope other than 0. So because of that, we refer to them as oblique lines. Now, these two types of lines here, horizontal lines and vertical lines, they're a little bit special because of the fact that for vertical lines, horizontal lines over here, notice the y value is fixed. It doesn't change, right? And for vertical lines, notice the x value doesn't change. All the points on that line have the same x value. So for example, just to use some numbers, imagine that here you have, let's say a is like 2, right? So this would be the point what? That would be 2, 0, right? If you go, let's say, 3 units up, right? What would that point be? Well, that point would be 2, 3, right? And if you go, let's say, 3 points down, so here you were at 3 and now you're at -3. So this ordered pair here would correspond to what? 2, -3. Notice something? The x values don't change. On this other one, let's say y value, the b value here, let's say that's like, say, 2 as well, right? So if I go, say, 3 units to the right here, right, or 3 units to the left, notice this point here would be like what? Well, first of all, the point here is 0, 2, right? This point will be 3, 2, and this point here would be -3, 2. Notice how the y values are all what? The same. So on these horizontal lines, the y value is fixed regardless of the x value. That's why if you notice, there's no x in the equation of a horizontal line. It'll have, like the one that we did, because we said it's at elevation 2, that would be y equals 2, the equation of that line. This one here, notice the x value is always 2, so we say x equals 2. That's the equation of this vertical line. Notice there is no y in this equation on the vertical line, because the value of x does not depend on the value of y. It's always going to be 2, right? Same here. the value of y is always going to be 2 regardless of the value of x. That's why you don't see any x in the equation, okay? So let's say we want to graph the line represented by y equals 3, right? So we know that if you want to make a table to do it, then the table is going to look pretty simple because something is never going to change. And which one is that? The y values. They're always going to be 3. So what x values should you use? Makes no difference. Just use the 3 simplest x values that come to your mind, right? Then if you graph those 3 ordered pairs, so you have 0, 3, 1, 3, and 2, 3 right there. So notice if I just graph the line that goes through them, it'll be that nice horizontal line. Again, that's 0, 3. This one here is 1, 3, and the one here is 2, 3. Okay? So notice that you get that horizontal line represented by this equation. Graph the equation x equals 2. Now, I mean, you could do this either by just reasoning, saying, oh, x equals 2, the x value never changes, so it's going to be a vertical line, and of course, it's going to go through x equals 2, like this, right? So there it is, right? Now, however, if you want ordered pairs, you can get that too. So here at first we graphed it just by reasoning. It's going to be a vertical line because the x value never changes, right? The x value is always 2. And notice for every point on this line, the x value of the ordered pair representing that point will be 2. Or if you want to make a table, and remember, one of the values in your table, one of your columns is going to be all the same number. Which one is it? You guessed it, the x. That's always going to be 2, right? So what y values should you associate with that? Any y values you like. For example, -1, 0, and 1. So look, here we have 2, -1 would be right there. 2, 0 is right there, and 2, 1 is right there. So here we have 3 ordered pairs associated with solutions of that graph. And that's the way vertical lines always work out, okay? So they'll always have the form x equals some constant. We usually just call it h, okay? So if you remember, we said that if an equation with 2 variables has this form, right? That was the slope-intercept form. Then the graph will be aligned, right? So remember, this is not a biconditional. So if an equation has this form, then its graph will be aligned. But it's not true that if a graph is aligned, then its equation has to be in that form. There is one group of lines which don't fit that, and those would be these ones, right? So these represent all non-vertical lines, right? So to describe all lines, you would need to throw in the vertical lines as well, right? And that's where those come in. So those represent the vertical lines, right? Now you have covered all lines. Notice that this particular group, that includes the horizontal lines too, because to be a horizontal line, you would just have to have the b be 0, right? And the m be 0, so you would end up with correct that. I meant the m be 0. The b can be any value, right? So if m is 0, for example, you get y equals 3, right? That's, of course, can be this line if we just let the m be 0 and we get y equals b. See? So this particular format can be obtained from this other form of the graph, right, of linear equations, but not this one. You won't be able to get that from this particular format, right? Because in this format, it's very important that the y does not go away. And if it does, you no longer have that particular kind of line that we're interested in, which will represent a function as we described earlier. And these particular lines here, the vertical ones, are the only group of lines that will not represent functions. All that will become easy to understand later. So we just noticed a little hint here that notice horizontal lines are going to have slope 0, okay? And again, once we discuss slope in general, all this will make a lot more sense. But right now, we're just trying to categorize all lines, right? So remember, the equation y equals mx plus b can be used to represent all lines except vertical lines. To represent those, we have to use this format. Next, we want to talk about what's called the rule of 4 for solutions of an equation. Basically, we can describe most of the solutions of an equation in this way, using either an equation, which is basically symbolically, using a table, which is a numeric representation, right? Using a graph, which is a visual or graphical representation, or you can use words, which would be a verbal representation. So the 4 ways to describe solutions are known as the rule of 4. So here we want to describe the solutions of this equation, y equals 4x, using the rule of 4. So that means we're going to do it using a table, using a graph, and using words. You're like, that's only 3. Well, because remember what the 4th one was? It was using symbols or equations. So we already have that, the y equals 4x. So that part is done. That's why we only do 3 other parts. So if we're going to do it using a table, we can just pick some values, right, for the x or the explanatory variable and evaluate the corresponding y values, and there we have our table. Of course, if we take those values we just found and plot them and do a nice line that graph that line that goes through them, we have represented it graphically. To use words, we're just going to, we know that basically all the solutions of this equation are going to have the form x comma 4x, right? So because the y value is always going to be 4 times the x value, see? So we can say for each solution, the y coordinate, which is right there, is 4 times the x coordinate, which is right there. And there it is. We've just used the rule of 4 to describe the solutions of y equals 4x. Now let's see if we can apply all this to a linear model. In the United Kingdom, nervous dental patients are sometimes given a sedative to calm them. And to administer the sedative, the dentist performs a cannulation, which involves inserting a thin tube into a vein in a patient's hand. In an experiment involving 20 individuals, researchers tested whether the amount of pain the individuals experienced during the cannulation, meaning when they put the thin tube in their veins on their hands, explains the level of anxiety that the individuals predicted they would experience by undergoing cannulation again. After undergoing cannulations, the individuals rated their experience of pain from 0 to 100, and their predicted anxieties about undergoing cannulations, again from 0 to 100. The patient's ratings are shown in the table. Now, with word problems, if you're really present when you read them the first time, you may only need one reading, right? But if we do a little trip to Maui here and there, and we get distracted in our minds, then we have to read it again and again. Sometimes you have to read a word problem 5 times before you know exactly what they're talking about, right? Especially some of the ones you encounter in statistics, they can sound really confusing sometimes if you don't pay complete attention. So if you need to read this again, read it again before you proceed. So here's the linear model in the form of a table. So we have the pain ratings versus predicted anxiety ratings, right? So here they are, the pain and the associated anxiety, right? Just like that. All right. Notice that each ordered pair is one result, so there are 5, 10, 15, 20 results here. So we're going to let A be the anxiety rating a patient predicts for undergoing another cannulation after having undergone one with a pain rating of P. Identify the explanatory and response variables, right? So we want to know how the level of pain affects the level of anxiety on the next one, right? So P will be our explanatory variable and A will be our response variable. Then we're going to construct a scatter plot and describe the direction of this association if there is one. And we're going to graph a model which is going to be a good fit model, best fit model for this particular scatter plot, and see if the model comes close to the data points. As we will see, it will. And we're going to use the model to predict the anxiety rating for a patient whose pain rating is 70. So as we mentioned, because they want to know the pain rating, how pain ratings explain anxiety ratings, P is going to be the explanatory variable and A is going to be the response variable. Okay, so then we're just going to basically do a quick scatter plot. It's very easy. We just basically take all these data values into something like StatCrunch, and it'll graph it for us very quickly, and we get this resulting scatter plot. Of course, you don't really need something as strong as StatCrunch to get a quick scatter plot. Any of these graphing calculators on the net, such as Desmos or ClassCalc, can get that done very easily. So what you would do is you would just put in all your data from the table. So I took the time to do that. So these are all these points. See, 3750, 6370, 82. You have to be careful because these pairs are these are ordered pairs, and these are linked, these two values. So you can't have them off at all. So 70, 81, etc. So basically I put all those points into, this happens to be Desmos. You can do the same with ClassCalc, for instance. And I also graphed, let me make this larger. So I put in these points from the example and the graph that they told us to graph. So this is the line they wanted us to graph. And if you notice, the line does in fact seem to represent these linearly associated data quite well. Okay, now we'll learn about this line in more detail. We've already seen it, and if you remember, it's called the best fit line, and we will visit it again in a couple of more chapters later. Okay, so clearly the association is positive, and which basically means the larger the anxiety level, the larger the predicted I'm sorry, the larger the pain level. Remember, the horizontal axis is the pain level, so the larger the pain level, the larger the associated predicted anxiety level on the next one. So here's that best fit line, which we saw a minute ago in Desmos as well. Does it come close to the data points? This would be definitely considered a really nice best fit line. Um, and let's see. Notice how it comes to close to pretty much all of them except the outlier, right? Where, you know, the individual had a high level of pain but predicted a low level of anxiety on the next future cannulation. So this one was a real outlier, which we basically threw out when we found our best fit line. So to use our model to predict the anxiety level for a person experiencing a pain rating of 70, if you remember, the model was right there, given by that format, right? So all you have to do is replace P with 70. So we get approximately 65.4 as the predicted anxiety rating for someone who had a pain rating of 70 on the first cannulation. So there's an application of this to linear models. That pretty much sums it up for us in as far as what we want to do in this section. And we'll just take a quick look at some of the problems from the homework, and we should be good to go. All right, so in this problem, we want to graph the equation y equals x minus 6. So my experience has been it'll be easier for me to graph these if I make the grid larger so I can see it. All right, so we know that we're going to be graphing two ordered pairs at least, right? So it's always good to do 3 as a check, but 2 is the minimum that you need. So because 2 points, if you recall, determine a plane. All right, since we're going to be very careful, we'll go ahead and do a pair. So, for example, if I let x be 0, y becomes 0 minus 6, which is negative 6. And I could do x equals 1, right? But that's going to make the point really close to that. It's going to be hard to graph it on here. So I'll move up a few. I don't have to do 1. I'll go to maybe 4. So when x is 4, I get y equals 4 minus 6, which is negative 2. So now I go to my line tool. And let's see how this is going to work. So we hit the line tool, and we're going to plot 0, negative 6. Notice that each tick mark represents 1 point, right? So 0, negative 6 should be right there. And 4, negative 2 should be right there. Now, okay, I think I need to go up a little bit, like so. Okay, so these become a little tricky to graph as far as just these dots are a little bit big. I didn't make the set, so I apologize on their behalf. I didn't write the program. So let's see if I place them in the right spots. Okay, so luckily I did. And That's all there is to it. That's how you graph these lines. Notice they also want you to find the y-intercept. Remember, again, we already did when we used 0 for the x coordinate. So we know that 0, -6 is going to be our y-intercept. So if you try to type in here just 0, -6, the system would not give you the happy face. So what you're going to do is you're going to actually use parentheses to indicate that you're typing in an ordered pair. So you're going to go 0, -6, and then you're going to close the parentheses, and now you're done. Okay? So that's how you handle a question like that. So in this next problem, we're going to graph this particular function, linear function, but notice it has a fraction in it, and they give you the specific instruction that they want you to use the y-intercept and one other point. So when we make our table, because of the specified fact that you need to find the y-intercept, we're going to go ahead and use x equals 0. That'll give us the y-intercept. So notice 1/6 times 0 is just 0. So there's the y-intercept. Now for my next point, I could pick something like x equals 1, 2, etc. But all of those would end up giving me fractions. So since I have no limitations on what values of x I can use, I'm going to get clever here, and I'm going to use 6 because I know 1/6 times 6 would eliminate the fraction and give me a whole number. So I notice that if x equals 6, y is going to be 1/6 times 6, which is 1. Like that. See, that's much nicer. So now I just go ahead and plot those. Let me make this slightly smaller. Okay. So 0, 0. Let me use the line tool first. So 0, 0 and 6, 1. We notice each unit does stand for 1 point. So, or I mean, each tick mark stands for 1 unit. So 6, 1 should be right there. Okay. Then we check the answer and we're done. Okay. So just in case you get a fraction, you should know how to deal with it. All right. So in this next one, we also have a fraction, and we can deal with that in a similar manner. So what we will do is we will go ahead and make our table. We'll go ahead and use 0 for x. Notice we end up with y equals 3/5 times 0, which is 0 minus 2, so -2. And now I could plug in x equals 1, 2, etc., but I'll be clever again and use 5 so that I don't end up with a fraction. So we have if x equals 5, that implies y equals 3/5 times 5 minus 2. These cancel out, so we get 1. Like so. So now we're going to plug those ordered pairs. So I don't know what this thing is doing up here. So I clicked something. Let me clear that. So we're going to do it properly now. So 0, -2. Let me choose the line tool. 0, -2 should be right there. And 5, 1. So 5, 1. Notice each tick mark does represent 1 unit. And that should do it for us. Okay? That's how you handle that one. So here's a special case graph. It's of course a horizontal graph, if you remember. And to get the points that we need to plot this, we recall that in this, for this line, the y value doesn't change. It's always -4, right? So all you need is to match that with a couple of x values like 0 and 1, and you'll be able to graph it very quickly. So we'll just go 0, -4, and 1, -4, and that should do it for us. There's our line. Okay, here's a vertical variety for this one. Of course, when we do our table, it's the x value that doesn't change, so that remains at -9. So we can match that with a couple of simple y values and go ahead and graph our line. So -9, 0. Oh, line tool first. Always forget that. And -9, 1. Okay, and that should take care of business. Okay. Okay, let's look at one of these multi-part questions. Worldwide sales of worldwide sales of particular phones are of a particular phone. One brand of particular phone is shown in this table for the last 3 months of various years. Let S be worldwide phone sales in millions for this phone for the last 3 months of the year, that is T years from 2005, and complete parts A through E. So when you set up your table, remember that you're going to be using T as the explanatory variable, and you're going to be using S for the response variable. In other words, the sales in millions. But of course, remember, you're not going to use, for example, T equals 2009, right? You're going to calculate that as a year since 2005. So for 2009, you actually subtract 2005 and you get T equals 4, etc. So for 2010, it'll be 2010 minus 2005 is 5. For 2011, it'll be 6, etc. Okay, so if you just take this data into StatCrunch, let's go ahead and sign in. You should be able to get that very quickly. So let's see. This one, it didn't drag it for me. Let me go back to my other graph and let's try that again. Open in StatCrunch. This time I should be okay since I have logged in. Okay, so remember, instead of 2009, we're going to use 2009 minus 2005, which is 4. And instead of 2010, we're going to use 5. For 2011, we'll use 6. Remember, just subtract 2005 from it and you'll get the value. For this one, we'll use 7, and for this one, that'll be 8. The year we're going to represent using T, and the sales we will represent using S. Okay, so going back to we were just supposed to do a simple, Okay, let's see. The explanatory variable is the year, of course, t, right? And the word while says is the response variable. Let's do our scatter plot to see which one of those we should pick. So remember, very simple, just graph scatter plot. Again, remember, you could also do that on ClassCalc or Desmos, very simple. Remember to use T for your explanatory variable, S for your response variable. The nice thing about StatCrunch is you can change the names to be exactly what you're looking for. There it is. Okay. So we go ahead and find that among the graphs given here, not that one. Let's see. Right there. Okay. So there we have it. Notice these other ones are very off. They couldn't possibly be the correct one. There's the one. And what else? Graph this model by hand on the scatter plot, right? So just so you can learn how to do this on Desmos or ClassCalc as well, you can do plus, add a table, put in the numbers the way we did into StatCrunch. So the thing with this is you're going to be stuck with X's and Y's for these. You can change those, but as far as graphing goes, you're going to have to make the association and use X and Y instead. So for 2009, remember, we're going to use 4. And then you can hit enter to go to the next spot. So we're going 4, 5, 6, 7, 8, and then you put the corresponding S values in the Y column here. So you have 8.9 and 16.2, 37.4. All this will not be boring if you're doing it along with me. If you're watching this like a video, this will be like the worst movie you've ever seen, right? It's like enough to make you want to go and take a walk or something. But if you're doing it along, then it can be fun. Okay, so 52.2, there is the scatter plot. So notice you have the scatter plot. Of course, this is not to scale, so you have to use the same scale on the X and Y to see it better or more like this one. But just to get you the line, you're just going to type in. Now be careful with this, because if you want to do that model which they provided, instead of S you're going to use Y. Remember, normally this would be, here you're using T and S, right? But normally the standard explanatory variable is X and the standard response variable is Y, right? So this would turn into Y equals 11.86 X minus 38.58 if you're going to graph it using one of these technologies. All right, so here we will type 11.86 X minus 38.58. And Y equals. Okay, so now let me make that larger. Okay, so, and let me hit home here. All right, now we can see the scatter plot and the line together, okay? All right. Now, and you can see clearly it's going to be the one that's chosen there. Does the line come close to the data? It certainly does, right? According to the model, estimate the worldwide sales of phones of this type for the last 3 months of 2014. Now, 2014 would correspond to T equals what? 2014 minus 2005 is 9. So remember, all you have to do is subtract 2005 from 2014 and you get the T value. So in your model, you're going to basically do 11.6. So the S value corresponding to T equals 9 is going to be 11.86 times 9 minus 38.58. Okay? So again, please be doing this along with me and this will become very easy for you. So here we can just type in 11, let's see, 11.86 times 9 minus 38.58. So we get 68.16. Let's see. And of course, when you round that to the nearest tenth, notice 68.16 to the nearest tenth will become 68.2. So where that's where that comes from. Choose a possible explanation for why. Let's see. According to the model, the estimated sales of phones will be this much, but the actual sales were 73.5 million, right? So why do you think that the model broke down here? Because there's a pretty big difference between 68.2 million and 73.5 million, right? That's more than $5 million difference, right? Million phones difference. So what could have happened? Well, of course, with iPhone every year, new model, Android, so probably a new model came out, and more people ended up purchasing than the model predicted. The model predicted that many, but since that new phone came out, they purchased a lot more. Compute the number of phones that were sold per hour throughout the day and night in the last 3 months of 2014 on average. Assume that there are 30 days in a month and the actual phone sales in the last 3 months were 73.5 million phones. So basically what we need to do is we need to go ahead and convert those days into hours, right? So that's what we're going to do. So let me show you how to use a unit factor to do that very easily. Okay, so the first thing we'll do is go ahead and write the 73.5 million in standard notation, which will help us understand it better. So we have 73, actually let me not write it there. So let's say we have 73.5 times a million, right? So that's 1 and 6 zeros. So basically that's going to take the decimal point on 73.5, move it 6 units to the right. So that's 1, 2, 3, 4, 5, 6, right? So we basically end up with 73,500,000. That's the same thing as 73.5 million. Okay, now we know that that many were sold. So 73,500,000 were sold over a period of 3 months at 30 days per month. That's 90 days, right? And we know that 1 day corresponds to 24 hours. So we use a unit factor in this manner. Notice that 1 day is equal to 24 hours. So the value here of this fraction is 1. That's why it's called the unit factor. And then we just have to just compute that. So we just go ahead and type in 73,500,000 divided by 90 times 24. And we end up with 34,027.7. If you round it to the nearest whole number, of course, it'll be 34,028. So on average, 34,028 phones were sold per hour during those last 3 months of 2014. And that's basically how you approach a problem like that. That would be an example of a modeling situation. All right, in this problem, we're given the graph of an equation, and we're asked to complete these ordered pairs. So notice they give you the x coordinates, and they're asking for the y coordinates. So I recommend you make these graphs nice and large so you can easily see. So basically, we want to know what value of y would be associated with x equals -6. So basically we go to x equals -6 right here, then we go straight up to the line, right, and see what y value would be associated with that, and we go from there, we go straight, we make a perpendicular to the y-axis basically. So remember, from here, go straight up till you hit the line, then drop a perpendicular to the y-axis, and you will see the point. So that would be like 3. So for here, for the y value, you would use 3. So when x is -3, you do the same thing. You go to x equals -3, go straight up to the line, and then drop a perpendicular to the y-axis, and you can see the y value would be 2. For 0, here is x equals 0, so just go straight up to that point, and you see that the y value would be 1. All right, so for x equals 3, notice the y value would be what? It would be 0 because it's right there. You don't have to go up or down, right? So it would be 0. And for x equals 6, notice that you would have to go down 1 unit, so the y value would be -1. Just like that. Type those in and you should be good to go. That's all you have to do there. Here's a similar type of problem, but in this case, they want you to find x when y is 2. So we go ahead and expand it. This time we're going to start at y equals 2, go straight to the line, right, horizontally. When we get there, we're going to drop a perpendicular to the x-axis, and we see that the x value associated with y equals 2 would be -2. Okay? Like that. All right. So here's a good problem that shows our understanding of some of this material. The graphs of equations 1 and 2, equation 1, equation 2, equation 1 in blue, equation 2 in represented by the red line, are shown here, and for each part decide which one or more of the points A, B, C, D, E, and F represent ordered pairs that satisfy equation 1. Equation 1 is the blue one, right? So basically you have to find out which of those points are on the blue line, because remember, the solutions of a given equation are on the line representing, or on the graph of that equation. So if you notice, the ones that satisfy equation 1, the blue one, would be F and E. For equation 2, which is the red one, think about it for a minute before you pause the video. Think about it, then come back. Notice it would be points what? B and F. Is that what I heard you say? In that case, you're right. B and F are the ones that would be solutions of equation 2. Which of the points A, B, C, D, E, or F satisfy both equations? Well, to satisfy both equations, they would have to be on both graphs. That means they would have to be a point of intersection of those two lines, right? So that would only be F, right? So which ones do not satisfy either equation? Well, they would be the points that are not on either of the two lines, right? So that would be A, C, and D. All right. Okay, so here's the last problem we're going to look at on this video. Notice they want you to find the equation of this horizontal line. Remember, horizontal lines have a very simple equation, and it has to do with the value of y that doesn't change. Notice the y value that doesn't change here is 7, right? For any x value, the corresponding y value is 7. So very simply, the equation of this line would be y equals 7. All right. So make sure you practice these. So far, the class has been more statistically oriented. From this point forward, it will lean more heavily toward algebra. So those of you who like algebra will be happy by that, and if you don't, maybe not necessarily, but you'll grow to like it. So make sure you do all the homework, and I'll see you on the next video.